So here we are again. Today we're going to start off with the circle and understanding that the circle can be used as a calculator, a universal calculator to calculate angle, wave number, and wavelength, just simply by using a circle and a straight line. So the universe is actually trapped within a circle. It's not trapped. It's in a closed system, and that closed system has an equilibrium that is completely equal to itself. Hence, the only shape that this can operate within is a circle or a sphere. A straight line which seems straight but in fact is curved. So, everything, let's say, that is calculated in this work fits inside of a circle. And the way I'm going to explain it is by simply using a beam of light, a straight beam traveling within a circle. Let us say that the inside of the circle is reflective, then the beam's going to respond a different way as it bounces around the inside of a circle. This just so happens to naturally calculate the angle of a pyramid, its wave number, and its wavelength, as mentioned before. So, in the slide you see now, illustrated is a circle. And always, in these examples, the circle being equal to the Planck length, measured by the circumference. So the Planck length being the circumference of a circle is required for these calculations to work. So you have the potential with the circle. And now imagine that there is a beam of light within the circle that has been directed from the center of the top of the circle downward to a random point in the circle. Remembering that the inside of the circle is reflective, this beam is going to be reflected in a certain way. So this beam represented in the picture is not actually random, but a specific angle used to illustrate this example. So as the beam hits the inside of the reflective circle, it bounces and strikes another part of the inside of the circle. And again, it will keep reflecting internally inside the circle, but creating a specific polygram form. And this polygram form is in fact these calculations unraveling themselves and auto-calculating the system. The calculation is finished where the beam ends where it begun, and it keeps on going around for infinity. This is a metaphor, but also a practical way to explain how these calculations work. So simply by doing that, it calculates the pyramid angle, the wave number, counting the waves where the beam strikes from 1 to 8, going around the circle, in this example, in a clockwise fashion. There are 8 wave lengths inside of this example. This beam in particular has created a total of 8 wavelengths. It has also calculated the wavelength value itself. So how is this to be understood? In the previous slide, you can see that the beam created a 45-degree pyramid. The wave number is simply obtained by counting the nodes that appear around the outside of the circle. And the wavelength, in this example, is quite simply the division. So the circle divided by 8. will give you the wavelength, which is the same wavelength as the circle itself, because it is just a reduced octave from the circle. The circle being 1 divided by 8 still equals 1 in the law of octaves. In this next example, I'll illustrate how angle can also be stacked within a circle, from the center of the circle coming outwards. This is an example of a 45-degree pyramid, again related directly to the Planck length. The circumference of the circle always being equivalent to Planck length for these calculations. And now the pyramid has been shrunken down so that the apex is at the center of the circle, going out to the edges of the circle. This is in fact the only accurate way to do a wave count for each pyramid. The polygram generator can double and half with the octave based off of its nature. However, you will always get the ratio of wave count within that calculation. The wave number will appear, but sometimes it is double or half the actual true value. The true value is obtained by stacking the angle of the pyramid back to back until the end meets the beginning. Even if it doesn't the first revolution, it will at some point. 45 degrees being the beginning, then stacking 1, 2, 3, 4, 5, 6, 7, 8. So we know for sure that this angle pyramid is exactly 8 wavelengths. Moving on to a 90-degree system, instantly it shows that 90 degrees has half the wavelengths, being 4 wavelengths. Depicted again, the wavelengths are counted on the screen, and the pyramid is measured from the center of the circle out to the circumference. And now illustrated are the angles. So in conclusion, we know that a 45-degree pyramid has a minimum wave count of 8, and a 90-degree pyramid has a minimum wave count of 4. These systems are the lowest wave count practically possible in regards to pyramid application, and are the foundations of how all other pyramids are derived. So that's the basic overview of this interesting calculation method. However, it's not really how you calculate these systems. It's just a reflection of a certain truth. The way that they are derived are simply by sending numbers on an X and Y graph, being addition and division. That is a way to unravel every possible integer in the known universe, simply by this method. Before I understood this method, I was playing around with different combinations, but as soon as I realized the answer was so simple, the integer map was the way, which will be illustrated in the next video. Now we'll move to a fun practical simulation to see how this plays out inside of a virtual simulation. And so this is the simulation, which depicts the beam which is traveling from this point, from a source, and traveling inside of a circle which has been made into an arc, but pretty much just a circle with a hole in the top for the beam to come through, and the inside of the circle being reflective, so that the beam travels down and bounces or is reflected around the circle until it meets the beginning. And this is very important to understand. It must meet the beginning for it to be a perfect integer. Otherwise, it's not. Another important thing to note is that the circle the circumference of this circle always represents, in this example, the Planck length. So this magical thing is like a polygram generator, almost, using this beside physics simulator, or just using this simulator in the way that I've configured it. It's a universal polygram generator for every possible combination. I have made this gap here a certain diameter to exclude high wave number modalities, because they're not actually useful, because they are too far away from the source, or the integer number is too high. So by broadening this diameter here, it prevents the beam from bouncing around too many times, and it's really just showing me the lower wave count modalities. So what's so magical about this thing, this setup, is that it is like a reflection of the universe being a circle, a closed system, and having modalities appear simply by the reflection of the closed system, the reflection of the beams inside a closed system. It's not exactly how it works. It has more to do with frequency and intervals, but this analog still reflects the same system. And what's so fascinating about this system is that if the circumference always equals the Planck length, this system calculates automatically, just with one beam, the angle, the wave count in number, and the wavelength. So it calculates the three variables automatically just by this reflective system, which I think is so cool. So just to explain that again, if this is the circumference of the Planck length, then the wave count, I'll start with the angle. The angle this is representative of a 90-degree angled pyramid. 90 degrees measured from the apex, shown in previous examples, which is one of the lowest wave counts that you can have in this polygram system. So this represents the Planck length anyway, because the 90-degree system is an octave of the Planck length. This is an octave of 360 degrees. Going around once, divided by 2 is 180, divided by 4 is 90. So this is a 4-division system. So this system is in unison with the Planck length. That's why I started with this system. So quite simply, by assigning this, it's telling me the angle here, it's telling me the wave count ratio, which is 4, 1, 2, 3, 4, and the wavelength, 1, 2, 3, 4. The Planck length divided by 4 is still the Planck length, because it's an octave of it. So it works the same with other modes as well, which I'll explain simply by adjusting the angle of this beam. There are a few exceptions to this system, and that won't be covered until later videos. However, all of the divisions I've been explaining are by one revolution only of the Planck length, whereas there are other harmonics and systems where you can have 3 revolutions, 5 revolutions, 7 revolutions, and so on to get different derivatives. But I won't confuse everyone too much just yet. So this is all based off of the first unit being the Planck length and its divisions. So the divisions created by simply dividing the circumference of a circle that represents 1 Planck length. So if we play around with this angle of the beam, you can see that the beam moves. You can see what I'm doing pretty much with the beam. So the beam is coming in from here, reflecting off of the surfaces of the inner surfaces of the virtual circle and ending here. So actually it's back to front, but it equals the same thing. The beam's coming from here and going back this way and shooting out of the circle. But it is the same thing. So if I adjust this beam, you can see what happens. And so as soon as the beam hits the inner part of the circle, it starts creating these modalities. And these are all of the modalities that can exist. There is more, but again, as I said, it is limited to closing this part of the arc. This actually allows more modalities, but ones that you would never use because they are too far off. And the wave count is too high. So simple ones like this one is related to 7 because you can see it has 1, 2, 3, 4, 5, 6, 7 wavelengths. It has 7 wavelengths, and I recognize this system. This is the derivative of 7. This is the second harmonic of the first one that has been illustrated, or I should say will be illustrated in the next video. So playing around a little bit more, we get complex harmonics that you want the wave count to be as low as possible. If the wave count is really high, then it basically means that it's a more complex system that is further away. Further away systems have less power and they're harder to manipulate. So if we go to this one's related to the numbers. Oh, what are we? No, this one's related to phi. So this will be depicted in the next video. This has a wave count of 10, I believe. 1, 2, 3, 4, 5, 6, 7, 9, 10. And this is a 72 degrees pyramid, which is directly related to phi. This is the first modality of that system. If we play a little bit more, find some more, there we are. And the equilateral system, which is the simplest system that can be derived, which is quite simply the equilateral triangle, a wave count of 3, 1, 2, 3, and 60 degrees. So we have the angle that's calculated, the wave number, and the wavelength as well, which is 1 revolution, 1 Planck length plus a third, which I'll explain how that's calculated in the next video. If we keep going down to steeper systems, we have something here. What's this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, I'm also familiar with this system. It's the second harmonic of the 11 division, which is a steeper pyramid. And if we keep going and we get back to the universal octave, which I've moved in that time from the 90 degree system to the 45 degree system. So I have moved 1 whole octave in angle because now we are on the 45 degree pyramid, which is measured from the apex. So if that's the apex, and it has a wavelength count of 8. So it is the beginning of the set that we use for pyramids. So I started at a 90 degrees pyramid and worked back to a 45 degree pyramid, which is represented here on the screen. And this is the Planck length once again. We keep going to ranges that we don't use because they're too steep. You get the second octave of phi, which the one I showed you previously related to phi is the same system as this. It's just that this one is 1 octave in angle more, so it is half that angle, which I showed before. As a result of that, the wave count is 5 instead of 10. And the wavelength is the same as well. But we don't generally use systems like this because they become exceedingly hard to manipulate for a multitude of reasons. But basically, it has to do with the internal dimensions of the pyramid being impractical for components and certain values going out of range. But you can still, there are still uses for these, but just not what I am focusing on explaining in these videos. And if we keep going, so this is again just a 36-degree pyramid. I keep going. Here we are, and the system of 7, which will be explained in the next video. And keep going to the system of, what's this, 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, the system of 9. And it keeps going and going. And what's this? 1, 2, 3, 4, 5, 6, 7, 8, 9. 11. Again, this is half an octave below the other system I showed, which was 11 also. And it keeps going until the beam will not, because it's now just shooting out of the circumference of the circle where the hole is. So if we go backwards to where we started, which was here, it's 90-degree system and the 45-degree system. So 45 degrees and then 90 degrees. And if we go backwards, the polygrams adjust slightly. So this is actually another system that's obviously out of range. Now the pyramids are too flat because that's, but again, you can build pyramids that represent this, but just not in the nature in which I am at the moment. This is a 108-degree pyramid, which again is the second harmonic of phi. And one of the systems which I've been focusing on the most out of all of them is this system divided by 2. So it is a 54-degree pyramid instead of a 108-degree pyramid, which is calculated differently. I will show you how that's done in future videos. But this is one of the most powerful systems you can use with the second harmonic divided by 2. Obviously, so it's 108 degrees here. Practical usage, you use the 54 degrees system. You keep going down to other systems. The hexagon, which again is an octave below the triangle, in 120 degrees measured from here to here. Keep going down. Yes, the system of 7, I think. 1, 2, 3, 4, 5, 7, which is an echo of how the star fits into here. The star of 7. Keep going. It's an octagon. Again, the echo of the 45-degree system, which is again another octave. That's what angle would that be? And it will go out of range again. Yeah. So if we play around a bit more and close this gap up, if I can figure out how to do this, I can show you that how crazy the modalities become. Oh, I've lost the beam. I know I can barely see it. The modalities just become, you can see more and more and more modalities. Literally, there are infinite modalities and infinite degrees of angle, and the beam's still escaping, but you can see, and it just clicks to, the universal ones again are the simplest. Then it will just spiral into the abyss. Here we are, another one. It's showed up. 1, 2, 3, 4. Yeah, system of 7. And the equilateral triangle. I think I've gone. Oh, there it is. And all the way to, yeah, some interesting effects. Actually, really cool. And like and we have like really, it's like super steep angles. Yeah, and if we close it even more, just to really see what can be seen. The diameter of this gap actually represents the highest possible wave count for, so it's kind of regulating that for this simulation. The wave, the approximate distance of here, well, the circle divided by that length will give you the maximum wave count it would show. So now we're up in the regions of just unusable mental systems, but very, this kind of spiritual, strange, thought altering patterns appear. I mean, it is kind of like there's something, I mean, just looking at it, it does something to the brain. It's like silences the ego and just allows you to, yeah, I don't know. It's like the aperture of a mind or an eye or something. But basically, yeah, so you start at the beginning of this dimension and you go, and then it just fractalizes to infinity, essentially. There was another effect I was playing with, which I thought was really cool now that we're playing around. Here we are, sorry. I forgot how to use the program, but there's some weird effects that I was playing with before that was tripping me out so much. Yeah, that was so cool. So, I mean, all this is just mathematics, but it starts creating like the craziest, interesting, like kaleidoscopic madness. That's like, that's just, this is because there's so much going on. The brain can't fully perceive everything. It becomes wondrous because it is like a dimension of, there's so much stimulation going on here. Yeah, you could really use some. So, oh, it's so intense. So there's multiple beams coming out here at once, creating echoes and all sorts of variables, and feedback systems, and it's very cool. Really is almost like it's alive. So all of this complexity is kind of how we perceive magic, when really it's just a form or a dance of mathematics, but reduced right down to its simplest building blocks. It is quite simply just modalities, very basic modalities. That make it all possible, but all rendered at the same time to make it seem like magic. Starting with this one, which is off the Planck system. So that's enough fun with the calculator, but essentially this is a simulation of how it works, and yeah, I hope you've enjoyed